So, hello everyone. So, here we will be discussing the last lecture of this module. So, this is bit different from the previous discussion that was on the heat transfer. So, in the last lecture we discussed the application of heat transfer in bioreactor operation, particularly during sterilization or maintaining a constant temperature. We discussed two different type of heat exchangers, double pipe heat exchanger and cell and tube heat exchanger, and cell and tube heat exchanger has provision of operating in a single pass or multi pass modes. So, in today's lecture first we will discuss what is scale up, then what are the principle of scale up, then followed by we will be discussing the different criteria which are followed for scaling up. The scale means size, up means increase. The scale up, as the name suggests, it is very much critical in biochemical engineering, because if you want to produce any product, we have to go from the lab scale to the large scale. So, it involves transitioning from lab scale to industrial scale production. Now, we have understood the scale up refers to the process of increasing batch size or production capacity to enhance overall productivity, and it ensures that process developed in the lab scale can be replicated at larger scales. Then how we increase the size? We go for the gradual increase. For example, on the lab scale to pilot scale of let us say 10 to 100 liter, and then we go to the further production scale that can be in the range of thousands of the liter. Now, why we need to have certain criteria for scale up? Because it has been observed that the product yield is decreases during the scale up, because the homogeneity could not be maintained of the lab scale and the production scale, and this results in compromising with the product yield and as well as the product quality. So, what are the principles which are followed during the scale up process? We need to maintain the similarity. It can be geometric similarity, kinematic similarity or dynamic similarity. Geometric similarity means related to shape and size, and dynamic similarity means related to flow behavior. Other option is one can consider the heat and mass transfer similarity at the lab scale and a large scale. So, let us refer the production scale system as a prototype and the small scale as a model. So, what is the fundamental requirement is the model and prototype should be similar to each other. Now, the first criteria is you want to have a geometrical similarity. So, model and prototype must be same shape, and all linear dimensions of model must be related to the corresponding dimension of the prototype by a scaling factor. For example, if I say constant aspect ratio means h upon d is constant. So, this ratio should be constant for both model as well as for the prototype. In the case of dynamic similarity, we maintain the ratio of flow velocity of the corresponding fluid particles is same in both in the case of model and prototype. In addition, the ratio of all the forces acting on the corresponding fluid particles are maintained same in model as well as prototype. When dynamic similarity of two flow fields with geometric similar boundary is achieved, so it means the flow field exhibits geometrically similar flow pattern. The whole idea is to maintain the similarity in the terms of size, shape and the flow behavior. To achieve, or rather you can say to replicate the same metabolic process or same biochemical reactions at the large scale. Now, what are the factors which affects the yield as well as the quality? The first is the inoculum. We require a seed culture, and when you go from the small scale to a large scale, both quality and quantity of inoculum are affected. Means you require a large volume of the inoculum, because typical inoculum size is 5 to 10% volume by volume. Further, when you go to the large scale, typically cheaper nutrient sources are utilized. So, it gives the sudden change in the media composition, because at the lab scale we mostly use the synthetic media, but at the large scale we are using a cheaper substrate. So, the culture requires a lot of time to adapt to this cheaper nutrient sources. In addition, there is a effect of nutrients on metabolic pathways as well. Third is the sterilization. So, for the lab scale we mostly use the autoclave for the sterilization, but for the large scale we need to go for the in situ sterilization. And in addition, when we are going for in situ sterilization, if there are heat sensitive nutrients, that may get adversely affected. In addition to the inoculum, nutrient and sterilization, there are environmental parameters like nutrient gradient, temperature gradient, pH gradient and oxygen gradient. And if these gradients are there, they are going to affect both heat and mass transfer. So, these gradients are typically absent at the small and well mixed bioreactor, but at the larger scale these gradients appear, and when they appear they are affecting the heat transfer as well as the mass transfer. Further, when you go for the large size, it alters the generation of foam, the shear forces as well as the rate of removal of this off gases like carbon dioxide. So, we have discussed different factors, and it is important here that variation in any of the above factors may significantly change the operational condition and consequently influence the product yield as compared to the small scale experiments. Now, there are certain operating boundary, particularly for the aeration and agitation. So, x axis is the aeration and y axis is agitation. So, if we have less aeration, so we experience the oxygen limitation. If you go for very high rate of aeration, you can experience the foaming. So, these are the two extreme, oxygen limitation and the foaming, or the oxygen limitation and foaming. Similarly, when we see this two extremes of agitation, if it is rate of mixing is very low, we observe a poor mixing, and when it is very high, it exerts the shear forces, and that may cause the cell damage. So, these are the two extremes, the poor mixing and cell damage of the agitation. And in addition, if you go for increasing the agitation, there is an increase in the cost because power requirement. So, the enclosed area is the desired region and outside zones are not favorable. So, you can say this is a permissible operation range, and in this range only this during the scale up it is important that this aeration and agitation value are selected from this region only. Now, what are the criteria for scale up? We will discuss one by one here. The first one is geometrical similarity. So, of course, we are trying to maintain all the parameters at the same value, but practically it may not be possible. So, what we will be doing, it is possible to fix the key parameters, and those parameters we are referring as scale up criteria. The first one we are discussing is geometric similarity. Let us say constant aspect ratio. So, we are saying h by d is constant. So, it should be h1 upon d1 equals to h2 upon d2. This ratio is constant, but if you follow this criteria, then it has been observed that ratio of surface to volume decreases during scale up. It means this interfacial area is decreasing, and which affects the mass transfer rate. The next criteria is power input per unit volume. So, if you remember the lecture on mixing or agitation, we have discussed the power is proportional to Ni cube di 5 for turbulent flow, and this is proportional to Ni square di cube for laminar flow, and volume is proportional to di cube. So, if I write P upon V, then for the laminar flow it will be only Ni square, and turbulent flow it will be Ni cube di square. So, it comes Ni square for the laminar flow and Ni cube di square for the turbulent flow. So, criteria will be, if it is laminar region, N1 square equals N2 square, and for turbulent region it will be N1 cube d1 square equals N2 cube d2 square, where Ni is the impeller speed and di is impeller diameter. Next criteria is constant liquid circulation rate. So, F upon V is constant. How the F is defined? F is defined as area into velocity, and area is proportional to di square and velocity is proportional to Ni into di. So, it becomes directly proportional to Ni di cube, and volume is proportional to di cube. So, F upon V becomes proportional to Ni. So, for this criteria it says N1 equals N2. So, we should say that the RPM at the small scale should be same as RPM at the large scale. The next criteria is oxygen transfer coefficient KLa as constant or constant Reynolds number. So, if you remember we have discussed the correlation that KLa can be determined experimentally as well as from the different empirical correlations. So, it was discussed that KLa is proportional to power per unit volume to the power a constant m into superficial velocity to power another constant n. Here u is the superficial velocity which can be calculated as flow rate upon area, and the value of m and n are dependent on the size of fermenter. So, depending on the bioreactor size, one can choose the value of m and n from this table. And second criteria is Reynolds number, we have already discussed. The impeller Reynolds number is defined as Re is proportional to Ni di square rho upon mu. So, it is proportional to Ni di square. So, if you want to maintain the constant Reynolds number, the criteria will be N1 d1 square equals to N2 d2 square. Now, next is constant impeller tip speed V. V equals to Ni di. So, the criteria will be N1 d1 equals N2 d2. And similar to this scale up criteria, one need to apply the scale down study also, because it is not possible to experiment any new trials or any change at the large scale. So, for any change we need to bring down the process to the lab scale and make the necessary changes. It may be the change in the media, it may be the change in the your production culture strain, or it may be change in the even this aeration and agitation rate. So, the testing need to be done at the small scale. So, for that the large scale need to be scaled down to try the new and innovative approaches. So, here we will see one example. So, let us say for a small scale the size is 80 liter and for the large scale the size is 10 to the power 4 liter. So, the first thing is the ratio of V2 upon V1 is 10 to the power 4 upon 80 equals say 125, and as we know V2 upon V1 should be proportional to D2 upon D2 cube upon D1 cube. So, we will get the value of D2 upon D1 as 125 equals to 5. So, we got di. So, if small scale its value is 1, so for the large scale di will be 5. So, we got the first thing from the given data of the volume. Now, second thing, let us apply the criteria. The first criteria is for the small scale P upon V was 1 and the large scale P upon V is again 1. It means we are applying the criteria. What criteria applying? Constant P upon V, and if it is constant P upon V, we can calculate. First we need to calculate the Ni. How we will calculate Ni? You consider it turbulent flow. The criteria will be then N1 cube D1 square equals N2 cube D2 square. So, D1 is 1, D2 is 5, N1 we are assuming 1, we will get the value of N2 as 0.34. So, we got the value of N2 as 0.34. Now, once this di and Ni is known, we can calculate the other parameter. For example, what will be the P? P will be proportional to Ni cube di 5 and it will be coming out to be 125. Similarly, the F will be, we have already discussed, F will be Ni di cube. So, F will be Ni di cube. So, the N2 we got the value of 0.34 and D2 is 5. So, we will get the value of F, and F upon V is directly proportional to Ni. So, what value we got for Ni? 0.34, that should be the F upon V. Similarly, Ni di, simple multiplication of Ni di, and the Reynolds number we can calculate as Ni proportional to Ni di square. So, this will be 8.5. Now, in the second case, this criteria is constant Reynolds number. What is the criteria of constant Reynolds number means? Which criteria we are going to follow? We are going to follow here N1 d1 square equals to N2 d2 square. So, the criteria is N1 d1 square equals N2 d2 square. So, the value of N2 will be 0.04, and once you got the value of N2, again we can calculate the power, we can calculate P upon V, you can calculate flow rate Fi upon V, it will be same as Ni, then Ni di, Ni is 0.04, di is 5, it will be 0.2. So, in this way you should be able to calculate the other parameter once Ni and di is known to us. Here we are following the criteria of constant tip impeller tip speed. So, here we are following Ni N1 d1 as N2 d2. So, if it is 0.5, the Ni will be 0.2, and once it is known we can calculate the other parameters, and in this case we are following the criteria F upon V as constant. It means F upon V is constant means Ni is constant. So, Ni was 1 here and Ni will be the same here. So, it says N1 equals to N2. So, N1 equals to N2, and if it is there, then power requirement will be Ni cube di 5, P upon V will be Ni cube di square, Fi will be Ni di cube, Fi upon V will be simply Ni, Ni di is Ni is 1, di is 5, and Re is Ni di square. Ni is 1, di square is 25, it is 25. Now, we see we applied 4 different criteria and a huge variation in the power requirement going from 0.2 to 3125. So, it says if you go for more and more power requirement, it's at the economic burden. So, depending on this we have to choose which criteria is economically feasible without compromising much with the product yield and quality. So, which criteria we should choose? So, it depends on 2 consideration, the nature of fermentation as well as the morphology of microorganisms. So, let us say if it is very much shear sensitive, then we have to go with, then we cannot increase the Ni, then we have to go with the constant tip speed if it is shear sensitive cells. And during scale up, now what is the objective parameter to maximize? You want to maximize, where you want to compromise with the power or flow rate or the Reynolds number. The traditional scale up is highly empirical and makes sense only if there is no change in the controlling region during the scale up, and in the empirical scale up, operating parameter for the large scale are often determined experimentally, let us say for hit and trial. So, we apply the different scale up criteria and you just see how it is doing with your objective, let us say product yield or the overall productivity, and then you can choose which scale up criteria is working better for your given system. So, scale up is very much essential for the chemical and biochemical processes, and it requires the careful planning, then testing and followed by validation. So, here combines theory, experimentation as well as the engineering judgment to get the best suited scale up criteria. So, I will stop here. Thank you.